Thank you, and thanks to the organizer for the invitation to this very nice workshop and very nice place. So today I would like to tell you about a very recent work we have done with Adele Javamard and Andrea Montanari, which appear essentially in these two preprints, and now it will appear in PNAS and another conference proceeding. So what is essentially the outline of the talk? I would like to start from a problem which has been already introduced by many of the speakers, which is essentially a community detection problem. I would like to convince you that spectral method may have some problems, and maybe optimization method based on another different kind of relaxation are better in terms of robustness, and at the same time are almost optimal. Then I will show you the performance of this SDP-based algorithm, just to convince you that it works very well. And then finally, in the second half of the talk, I would like to convince you that we can even compute the algorithmic threshold for this algorithm. And so it's robust and quasi-optimal in some sparse, difficult cases. Okay? So I don't have to convince you that the community detection problem is interesting, because half of this audience is studying it, so I will skip this. But let me just focus on two features that, in my opinion, are essential. So we want a community detection algorithm to be optimal in the sense that when you run it on a random ensemble, it detects the hidden community as soon as it can. But at the same time, you want to be robust. So if you take a random graph and you perturb it, you want the algorithm to return an answer which is close to the one in the purely random case. Okay? Otherwise, it would be difficult to use it in real data. Okay, so as a benchmark for the purely random case, I will consider the stochastic block model, which has been already defined by many of the speakers, Chris yesterday and also today Mark. And so this is just to show you my notation. So we consider n nodes and q groups of equal size, and then you put edges with two different probabilities depending whether the two nodes belong to the same group or different groups. And I will stick mostly to the assortative model, where the inner connectivity is larger. Okay, so essentially this is the problem, problem I'm focusing on to convince you that is interesting to study. So you take an adjacency matrix and you fill it the red region denser than the orange part, but then you remove the colors, you remove the ordering, and you ask someone to recover from this unordered and unlabeled adjacency matrix the original matrix with the communities. Okay, so this is our problem. And in my notation, I call x naught the true partition, so the one you build into the graph, and x hat is the estimated partition returned by different statistical estimator, and we measure the quality of the inference via this scalar product between the original and the inferred partition. Okay, so this essentially is the fraction of nodes correctly identified by the inference algorithm. Okay, so what are the relevant parameters? I will mainly concentrate on the q equal to equal size stochastic block model, for which we have very nice result on the bias optimal inference. The two relevant parameters in these problems are the mean degree and the signal to noise ratio. Okay, so the mean degree essentially is telling you how sparse is the problem. So if D is very large, the problem is dense and is somehow easier than the problem in the very sparse regime. And the signal to noise ratio is such that you can prove that in the bias optimal framework there is a threshold phenomenon at lambda c equal 1, such that for lambda smaller than 1 is impossible, informatically, theoretically impossible to detect any hidden partition, while for lambda larger than lambda 1 you can, and actually it has been proved that an algorithm based on belief propagation can return an overlap larger than 0. Okay, so this all this has been obtained by very ingenious spectral method that Mark today told us about. But the question is essentially, what happens if you don't know exactly the generative model? So all this can be done if you know the generative model underlying the graph that you are working on. But if you have no information about the generative model and you only know very few things, for example, that the model is assortative, so nodes in the same cluster are more connected than nodes between clusters, and for example that you have two equal size groups just to make computation easier, the best thing you can do is to maximize the likelihood, which actually amounts to maximize this quadratic form subject to the constraints that the sum of the variables is equal to 0 in order to satisfy the two equal size group. The problem is that this problem is NP-hard. This is essentially the mean cut problem discussed by Dembo yesterday, and so you have to relax this problem to make it tractable, otherwise you are not able to solve it. So let me rewrite the problem in a Lagrangian formulation. So you want to maximize this function fixing this constraint, so introduce a Lagrange parameter, and as long as the Lagrange parameter is large enough, the maximization of this Lagrangian happens at the point where the sum of the x is 0. And in particular, if you take this Lagrangian parameter, which is equal to the mean degree of the graph, actually you can define this centered matrix, which is nothing but the matrix minus the average value, such that the mean value of the matrix is 0, and then you can maximize this quadratic form without the constraint. Okay, so this is what we would like to do. Still, this is NP-hard. It's just a reformulation of the problem of the previous slide, and so we have to start with some relaxation. Otherwise, the problem is unsolvable for very large n. So, what spectral relaxation does, essentially, it tries to maximize this function. Instead of maximizing on the set of all these discrete points, it maximizes over the entire hypercube, which is a convex space. So you can easily maximize this function, and then you compute this amounts to compute the eigenvector, the principal eigenvector of the centered matrix. And once you compute this principal eigenvector, you project back in one of the vertices of the hypercube, which is one of the set of possible solutions, by just taking the sign. All this is fine as long as all the components of the principal eigenvector are similar. But if the principal eigenvector starts to have components very different, this projection is unlikely to give you the right result. And indeed, this is actually what happened if you look, for example, you do PCA on a sparse matrix. As long as the degree is very large, you see that the component of the principal eigenvector are very much correlated to the partition. The blue and the red are the two different partitions. While if the degree is very small, if the degree is very small, then you have localization, and the component of the principal eigenvector are more or less useless for understanding the underlying partition. So the reason why this happens is well known. If you can write the centered matrix as a rank 1 matrix bringing the signal plus a random matrix. And if you study the spectrum of this random matrix, you realize that, well, for large D you have this Wigner's semicircle law, but for small degrees you have a tail with localized eigenvector. And this is where the problem comes arise. So PCA fails for this reason. People know this, and so invented new spectral method, but all the methods based on the adjacency matrix, they are suboptimal, and in particular you can prove that many of these has a threshold which is strictly larger than 1, until very recently all these authors propose a new spectral method which is much better, in the sense that, well, I don't want to spend too much time on this because we already heard the talk by Mark on this, but essentially this new matrix avoids some kind of localization, essentially because you do non-backtracking path, so you are not going forward and backward on the highly connected nodes. And thanks to this, you can prove that these two algorithms for non-backtracking matrix and the Bayesian, which is equivalent and much easier because this matrix is symmetric, so all the spectrum is real, they can achieve optimality. Okay, so this is very nice. Unfortunately, if you try to apply this spectral method, which are optimal for random graphs, on non-random or quasi-random graphs, you realize that there are some problems. In particular, let me define this quasi-random graph in the following way. You generate a graph according to the stochastic block model, so a purely random graphs. Then you choose a very small subset of size alpha of nodes, and you build a clique around each of these small fraction of nodes. And you expect, since the number of edges that you are adding is a fraction alpha times d, you expect that if alpha is much smaller than 1 over d, the result of the inference method should not change. It should not be, let me say, should not modify sensibly by the addition of this tiny fraction of edges. Unfortunately, this is not what happened. And suppose that I'm looking here to the inference provided by the Bayesian, just because it's much simpler. It's a symmetric matrix where you have to compute the second eigenvalue and the second eigenvector. The second eigenvector is this one, and as you can see, is in the case with no cliques added, is very much correlated with the partition. Okay, so the eigenvector is very much correlated with the partition. Look, that we are on a very large graph, very close to the threshold, so 1.1. The threshold is at 1. Indeed, the overlap is small, is less, so 39% of the nodes are correctly identified. The problem is that now, if I add a very tiny fraction of cliques, so in this case alpha is 10 to the minus 3, so is much smaller than 1 over d, which is 1/3, what happened to this eigenvector is that it gets localized. And so essentially the overlap with the original hidden partition is practically 0. Okay, so this is just the second eigenvector, so I ask myself, maybe the other eigenvectors still bring some information. Unfortunately, if you look at the entire spectrum, these are the eigenvalues, what happened is that all this negative tail is due to this newly added noise on top of the random graph. And so even if you look at all these 30 eigenvectors, none is bringing information. You have to move into the bulk, okay, but then you have to start digging into the bulk in order to find an eigenvector which is bringing information. Is not very convenient, okay? So this is the problem of the spectral relaxation. So let's, yeah.
So we thought about this a little bit with the non-backtracking paper, and I mean, it's a little bit of a philosophical issue, right? So these cliques are very small, but they're also incredibly dense compared to the rest of the graph. So, you know, at some level, the fact that a community finding...
Here, consider that the clique tibia is 4 nodes.
Oh, all right. Well, that is really very small.
So,
okay,
I won't say that it's so dense.
Well,
These are 4 nodes forming a tetrahedron. So I essentially added less than 100 tetrahedrons in a graph of 10 to the 5 nodes.
Okay. I guess I'm just trying to say that cliques are communities that would jump out at you.
Yeah,
so,
but I don't think that
you know,
to reconstruct groups of 4 people.
Essentially, these 30 eigenvectors are each one localized on each of the cliques that you put.
To be fair, this is exactly the case that was looked at by Marc Lelarge 1 hour ago, right?
Yeah, but he modified the algorithm because he knows what is the perturbation.
Here you should modify the generative model in order to take into account that, and then if a new noise arrives, you have to modify it again. And you can do everything, but you have to make a much more general ansatz. So let's see what we can do without to rely on the generative model, okay? So we try to do a different kind of relaxation, an SDP relaxation, semi-definite programming. So again, we start that we want to maximize this quantity over this discrete set, which is equivalent to maximize the trace of A centered at time x, subject to the fact that x is positively defined, so all the eigenvalues are non-negative. These are an n times m matrix. On the diagonal, xii is equal to 1, and x is of rank 1, because essentially is the outer product of x of small x by itself, okay? So this formulation is equivalent to the original formulation. And now SDP relaxes the rank. So instead of looking for the matrix X of rank 1, maximizing this function, this linear function, because now is a linear function in the matrix X, we relax the rank and we maximize this trace of A times X over the convex space of all over the cone of all the positive semi-definite matrices. Okay, so this is a convex optimization problem, and once we find the maximizer, which now is a matrix of rank m, where m can be between 1 and n, we have to project it back on a rank 1 matrix, and I will explain you in the next slide how we do it. So why do we expect this to be better than the spectral relaxation? Essentially because among the matrices that we are studying, we are sampling in order to maximize this linear function, we are forcing all the diagonals to be 1. What does it mean? Suppose that this matrix now is representing the outer product of the true hidden, well, the inferred partition with itself. The fact that along the matrix is 1, this doesn't allow the vector small x to localize, because if it gets localized on the diagonal, you will have heterogeneity. You will have the diagonal elements which are very much different. So you are in some sense forcing the system to produce a solution which is homogeneous over the graph. Okay, so you avoid the localization. Now, how do we do this in practice? So in practice we have to look for the maximum of a linear function of a huge space of all the matrices, okay, and we want to do it in an efficient way. So first of all, you realize that the rank m semi-definite, positive semi-definite matrices can be written as correlation matrices between variables x having m components, okay? This immediately gives you a matrix which has 1 along the diagonals, is positive semi-definite, and so you just have to work in this reduced space of matrices where m now is a parameter. You can set it very large, very small, and I will show you that you can play with that. Okay, and then so you try to maximize this quantity, which is nothing but the scalar product between vectors of m components subject to this constraint, and we do it in the simplest possible way as physicists would do it, so zero temporal dynamics. So at each step we take one variable and we align to the local field. In this way we are doing steps that at any steps we improve, we increase this quantity. Okay. Finally, once you find the maximizer, which is now is a vector of n m component variables, you compute the empirical covariance matrix, you compute the principal eigenvector of this matrix. So the idea is that in the solution, most of these vectors, so suppose that you have, let me say, a cluster which is very much connected in this part, and these are the two communities. The idea is that once you find the optimizer, most probably most of these m component spins are roughly aligned in this part and roughly aligned in the other part, and maybe some spin in between is not aligned. Okay, so once you see this blue configuration, you want to understand what is the principal direction along which you want to project the eigenvector. So you compute the empirical covariance matrix that gives you a direction which is this one, and then you project and you put all this to -1 and all this to +1. Okay, so this is This is the idea. And if you want to play with the code, you can find here a publicly available code, which I hope is clear enough to be used. Okay, so obviously this algorithm depends on the parameter m. So we are working with spin with m components, and in principle we obtain the SDP convex objective function only when m is equal to n. While if we stick m equal to 1, we have the original maximum likelihood problem with discrete variables. Okay? So you see that the same function changes drastically when you change this parameter m. For m equal 1, you have a very rough objective function which leads you to an NP-hard problem. For m equal n, you have a convex objective function, but actually you don't need to go to m equal n, because already for m larger than square root of n, you can prove that there are no local maxima. In particular, recently, Andrea also showed that for any m value, all the local minima are close enough to the global minima by a factor 1 over square root of m. So the idea is that even for m small, this algorithm may work very well. Okay, because the function you want to optimize is no longer so rough, so maybe you can optimize it easily, and still the algorithm is much faster because it's linear in m. Okay? Okay, and the running times is very mild in the size of the system. So let's see how it works. Okay, so now I'm taking a stochastic block model, very sparse, very close to the theoretical threshold, and with no clicks at all. And the red line is the expected best overlap that you can achieve via bias optimal, because it has been computed via the Bethe-Hessian. Okay, so this is the best you can do in this problem. And you can see that if I...
The best you can do should be obtained with
BP.
Right?
Okay, I'm lazy. I run Bethe-Hessian because according to your paper it's very close to the optimal. You are right. So maybe the optimal is slightly above, exactly where we go with this data. Indeed.
Beats the optimal. Positive fact.
Okay, so this is the result of a typical spectral method, the most economic to use, the one that I used. Now, if n is equal 1 or 2, you see that during the time of the algorithm, you are not able to achieve the optimum. You get stuck in some local maxima. But if you increase m, the convergence to the global maximum is faster and faster. But you don't need to go to m very large, like here, this is 64. Even for m equals 6, you approach very closely the global maximum. So you see that this objective function, already for rather small values of m, is very smooth.
Just out of curiosity, if you do m equal 1 but not 0 temperature, if you do simulated annealing, where would you be like on this figure?
At this value of lambda, I don't know, because we are quite close to the critical point. I never run simulated annealing on this problem.
It's not so bad. I mean,
certainly better than this, because this is zero temporal dynamics, so this is the worst you can do. By simulated annealing, you will grow a little bit, but exactly where you go, I haven't run it, so I cannot answer.
So here is time normalized by the number of vertices or not?
Yes, so essentially here I updated 1000 times each vertex. But I will show you also actual times, and it's very fast.
Do you have a sense of the asymptotic number of dimensions that would be sufficient to get close to the optimum? Like should m scale like root n or log n?
Well, here you see that for this size, square root of n is already 200. But we have a very good result even for m equal 8. So it's clearly not scaling with n. What I can show you is that if you run this with different size of the system, essentially the values of m that you need don't scale with n. So they are really finite, or maybe scale like log n, but it's really enough to have very small values of m to the algorithm work perfectly well. And the good news is that it's very robust. So now we add a 10 to the minus 2 fraction of click in the way I explain you, and while standard spectral methods are not able to detect the more hidden partition, essentially you see that the two curves obtained for m equals 16 and 16 and 64 essentially don't depend on the value of alpha. So it's practically insensitive to the newly added noise. And moreover, it's extremely fast. If you run it on this laptop for a size 10 to the 5, you need a few seconds. So you can solve a convex optimization problem with a million of variables in few seconds on a laptop. This is why we don't compute any gradient, we don't compute any Hessian, we just do single variable update, and this is extremely fast. Okay? Now let's go to the second part of the talk, where I would like to convince you. So this SDP-based algorithm is fast, robust, and now I want to convince you that it's quasi-optimal. So if we run it on a random ensemble of problems where we know where is the optimality, I would like to convince you that we are very close to the optimality.
So maybe, how is SDP using the same that Verschanin and his collaborator? So they also prove some robustness, right? Is it different what they prove?
You can.
They prove in that paper.
Which paper are you talking about?
But okay, some robustness is kind of obvious. In value, it's obvious, right?
Yeah.
That if you change epsilon fraction of the edges, then the value changes at most by fraction epsilon.
Here is an optimization problem. So if you change.
Also for the optimization, I think. Okay. Yeah.
But then.
The
value of the objective function, if you change the objective function by epsilon, I cannot change more than epsilon.
I understand, but it's
so.
because of the optimizer. They moved it so far. Okay, we should.
So, what is the main thing that we would like to prove is that it exists a threshold for this algorithm, for SDP algorithm, between a phase where essentially you cannot detect anything to a phase where you can detect something. And actually in our paper we proved this first in a simpler synchronization problem where the matrix Y that you observe is dense and is made by summing a rank 1 matrix with a random matrix, which is the noise. And lambda represents the noise to signal to noise ratio, and depending whether X are real or complex, according the W matrix is filled with Gaussian or complex Gaussian numbers. And from the observation Y, you would like to infer the signal X, and you can do it using different statistical estimators. So you can do bias optimal by marginalizing over the posterior. You can use maximum likelihood by computing the argmax of this function, this quadratic function, or you can do SDP, which is what I just told you. So find the matrix X such that it maximizes the linear function trace XY in the cone of semidefinite positive semidefinite matrices. The nice thing is that okay, and you can convert this again as a problem of maximization of a new function where the variables X now lives in a m-dimensional space. The good thing is that all this can be plugged in a single unified framework in statistical mechanics. Okay, so essentially we study just one statistical mechanics measure, and from this, taking different limits, we can recover all different statistical estimators. Okay, so the goal now is to understand what happened to this measure, and from this we can infer the outcome of different statistical inference. Okay, and without surprise we get the Sherrington-Kirkpatrick model that is always under the gun. So in particular for Ising variables, when you study this function here for real variables, is equivalent to study this Hamiltonian, which is the Sherrington-Kirkpatrick, where the couplings have a non-zero mean proportional to the signal-to-noise ratio, and a variance which is 1 over n. Okay, so the idea is that here the signal is the magnetization. So if the if the measure has a non-zero magnetization, then it means by that measure you can identify the hidden partition. Okay? And for example, in the temperature lambda phase diagram, you have a phase which is the paramagnet where you cannot identify anything. Indeed, it happens for small lambda. You have a phase, a ferromagnet, where the magnetization is non-zero, and so you can identify the hidden partition. And you have a phase, the spin glass, that you want to avoid because it's NP hard. Okay? Now, the bias line passes here. Actually, the full phase diagram, it should consider the breaking of the replica symmetry. And what we know from the solution of the Sheridan-Kilpatrick model, so we don't have to solve again a model, is that we have a phase transition in lambda critical equal to 1, but while in the bias case it happened between two replica symmetric phases, so we can sample easily the measure. At zero temperature, which corresponds to the maximum likelihood estimator, the phase transition happened between two phases which are replica symmetry breaking. So it's unlikely that we are able to sample correctly the measure in a polynomial time. Okay? And so this makes the maximum likelihood estimator NP hard. Okay, so we solved this model in the dense case by these ansatz, essentially. So the main ansatz, it works like this. It says each variable locally fills a local magnetic field xi that changes from site to site. So xi is a random variable, is a Gaussian random variable, and moreover he has the correlation, the local correlation are controlled by a matrix Ci, because now locally you have a m component variable, so you the local correlation are controlled by an m times m matrix, and what you find essentially is that in the thermodynamic limit this quantity does not fluctuate, so it can be described by a unique matrix C, and this quantity is a Gaussian vector that is fully described by the mean vector mu and by the covariance matrix Q. And so you finally write self-consistency equation for these three objects, a vector and two matrices, and you solve this at different values of lambda and m, and you find the solution. And then the solution looks like this. I'm plotting here the mean square error, so the expected value of the the distance, this minimized over the symmetries, but is the distance between the inferred partition and the original partition. And you see that for lambda smaller than 1, you cannot do best than a random guess. And then at lambda equal 1, you have a phase transition, and the mean square error decreases, and the blue line is what we get by SDP, which is quite close to the bias optimal, which is the red dashed line. And definitely much better than PCA, which is the blue dashed line, because at large lambda values, PCA is not exploiting the fact that the solution must be on the integers. So it typically finds a solution of the vertices. Okay? And the points are numerical simulation that you see that already for not so large sizes are very close to the thermodynamic limit. So it works quite well.
So we're a step or two away from the block model here. Should I think of this as these analytic calculations are in the dense limit of the
This is
block
dense
model?
limit. I will show you the stochastic block model in a minute. Okay? So now, stochastic block model. Okay? This is the answer to your question. We did two things. First, we run the SDP-based algorithm. So we take the algorithm, we run it with a very large value of m. So like if we are really doing SDP on the cone of positive semi-definite matrices, if m is large enough, there is no dependence on m. But since this is quite heavy to do, because we know that the algorithm is very fast with very small m, but if you take m 100, well, it takes some time. Then we also propose an approximate ansatz which is exact in the large D limit and still provides a quite good answer also for finite D. So I will show you the result of these two. So this the result for the stochastic block model with D equal 5 and this lambda, the signal to noise ratio. So the idea is that up to a certain critical value that we have to compute, the overlap is 0, then becomes different from 0, and the points are what we get running the algorithm, the actual algorithm, and the black line is the approximate analytical solution. So I would say that is approximate very well, at least here. Then close to criticality, we have to be careful because now let's try to compute better the critical point. How do we do? Well, essentially we run the algorithm, the actual algorithm, for different sizes for many samples, because as you know who did simulation of the disordered system, there are huge sample-to-sample fluctuation. If you want to achieve a very high precision, you have to run a huge number of samples, and this is a quantity called Binder cumulant that must cross at the critical point. And so you see they are indeed crossing, and if you zoom and you run even better simulation with larger sizes, you see that the crossing of the actual behavior of the algorithm is very close to the number we get from the approximate analytical solution that I will describe you in the next slide. And so these are our best estimates for the algorithmic threshold for SDP run on stochastic block model with mean degree 5. Which does it mean? That is able to find the hidden partition as long as lambda is larger than this value, which is less than 2% worse than the optimal one, which is 1.
How sensitive is this to D? If I take D to be 1?
I will show you the plot. I already have the answer to your question, I hope so. Now, the approximate analytical solution. If you want to solve this problem, in principle, you want to solve the BP equation for this problem, at least at the replica symmetric level. The problem is that we are working with variables living on a m-dimensional sphere. Okay, so you would like to parameterize with few numbers, as in a good mean field approximation, the measure of a sphere. This is not easy. Okay, and so I'm writing here the most general ansatz we use that already contains quite a good number of parameters. And the idea is the following: since we are interested in the situation where the OM symmetry gets broken along one direction, because if we identify the signal, the symmetry gets broken, immediately from the beginning we take the variables x and we divide in two sectors. One variable s along the direction where the symmetry will get broken, and an orthogonal vector in a m1-1 dimensional space, which looks like the random part, the random orthogonal part. And then on S, we use, well, always the exponential, we use a quadratic function, and on the orthogonal part, we use the same answers we use in the dense case. So essentially, the measure depends only on the scalar product with a random vector. And then we try to close, and the random vector is a Gaussian with this distribution, and then we try to close on the number C, H, and R, which are our three parameter per site. Okay, these answers should be correct in the two limit, in the two extremal limit, high degree and degree close to the percolation threshold. Then you take this ansatz, you plug into the cavity method, and you derive self-consistency equation. You solve by population dynamics, and you compute the mean overlap with the true partition function. And what you get is something like this. So it's 0 up to here and different from 0. So it works quite well. But even better, now, since I would like to understand when this becomes different from 0, I can do some kind of linear approximation, because here all these parameters are small, some of these parameters are small, and so if you do linear approximation in H, which is the quantity which is small, you can convince yourself that the R, which is the term of the quadratic term, is 0, and so you end up with simpler equations which are linear, and so you can try to understand when this linear equation becomes unstable, which corresponds to the critical point. And doing this, well, this is the solution. I will show you just this. So this is the rate actually is this quantity here. So it's telling you the rate of growing of the linear part. So as long as it is 0, the symmetric fixed point where the OM symmetry has not been broken is stable. Beyond this point, the OM symmetry gets spontaneously broken. So this is the critical point for the appearance of a non-zero magnetization in the direction of the hidden partition. And so this is our analytical approximate estimate of the critical point. You can compare the red points, which is what we compute with running the actual algorithm, with a black curve, which is our estimates through the analytical approximate solution, and the two are quite close. Consider that for large D they must coincide. So here everything is going fine, and here they are quite close. And most importantly, with respect to the optimal threshold, which is 1, we are always less than 2% off. So this algorithm for the stochastic block model can recognize the hidden partition in the worst case when lambda is larger than this curve, which is not more than 2% towards the optimal value. Okay, I think that it's time to finish. And so let me just recap the take-home messages. These are especially for physicists, so I'm thinking what I would like to know 2 years ago before starting working on this. So SDP relaxation are extremely effective. I didn't know this before as a physicist, and I think that many physicists are not aware of this. They are robust, quasi-optimal, and they may also outperform spectral relaxation in many cases. Even better than SDP are SDP-inspired algorithms. So if instead of using m equal to infinity, use small m, this is even better. And obviously doing the theory for that maybe is harder, but for practical application is extremely powerful. Finally, another take-home message for physicists, we have to study these models with m component variables, because we know much less than the easing models, but they have a different physics, and most probably they will provide us with better algorithms. So, okay, it's much harder, but it's worth doing it. And I thank you for your attention.
Questions?
Already many.
There are proofs of algorithms with good theoretical guarantees for solving these kind of relaxations that that work with the constant dimensional vectors, and where the evolution is. I'm not sure how it's related to your evolution, like the way of
I didn't explain well how do we evolve the.
Right,
so how do we maximize the objective
right,
function?
But it's a pretty simple evolution. Basically, it's also related to continuous time random blocks on the graph. Did you?
No, we.
See or did you try to see?
I didn't know this work, but what we did is a very simple updating rule, but it's very effective, because you have to maximize this function in n variables with m component each, so it's not an easy object. The problem is that if you start computing a gradient, it takes quite a lot of time, even computing the gradient, even in the sparse case. So actually, what we do is we take. We do the following. At each time, you can compute, consider this variable which is interacting with other variables, and each variable has its own spin in a m-dimensional. And so all these variables are producing a field on this variable here. And at each time, regardless of the value that this variable has at this moment, we compute the local field, which is maybe here is something like this. I don't know if there is a majority pointing up, and we align the variable which is of unitary norm with the field. This is actually very fast. It's like saying we do a coordinate-wise ascent, but with the advantage that on each coordinate we already know where is the maximum. So on each step we maximize in one coordinate. While when you compute a gradient, then you have to do a step. You don't know where is the maximum. You should compute the Hessian, but compute the Hessian is impossible because it takes too much time. So if you don't want to compute the Hessian, then if you use the gradient, you have to do a step, but adaptive step, you don't know where is the maximum. Here you are doing something much simpler. So you take one coordinate, you maximize. One other coordinate, you maximize. And in n steps of this, which is our, let me say, one Monte Carlo step is n update of this type, you do better than going along the gradient. And it takes more or less the same time, because computing one gradient is like doing n of these updates. And so this makes the algorithm extremely fast. I think it's different from what you were saying, but with respect to, we program different way of maximizing the function. This one looks really the fastest.
So is the key feature that you normalize? So once you know the direction, you go in a big step, even if the direction is small, or is the key step that you do?
We align the variable. The variables are all norm 1, because otherwise the diagonal of the matrix is not 1. So we take the variables which are norm 1 and we align to the local field, and this is the best you can do. So in this way you are maximizing the objective function coordinate-wise.
It's block coordinate ascent.
I don't know where the block comes from.
Because
but
block you update m variables.
Ah, for that. No, for me it's one variable. It's an m component variable. Now I understand where the blocks come from.
Any other questions? All right, let's thank Fedrico again.